Physicist Jim Al-Khalili demonstrates that time can be stretched or squeezed. He uses a theoretical light clock located on the dashboard of his car. This device bounces a beam of light up and down inside the car, which is traveling close to the speed of light. The different way in which observers inside and outside of the car view this light beam demonstrates that they experience time at a different rate.
For me, travelling with the clock inside the car, I always see the light beam moving vertically straight up and down.
If Al-Khalili's twin brother watches from the roadside, he would see the light beam follow a different path. Combine this horizontal movement of the car with the vertical pulse of the light clock, and one thing results.
For me, standing watching the car go by, I see the light beam travel diagonally.
The distance light covers is greater for the viewer outside the car. But crucially, the speed of light is the same for both. Time equals distance divided by speed, so the time passed is less for the person who is traveling in the car. Time actually passes more slowly for the person who's traveling at speed. Scientists call this time dilation. Geneva, Switzerland. This is CERN, the European Organization for Nuclear Research, home of the world's largest particle accelerator. Scientists from 85 different nations study the subatomic world to understand how the universe works. At this space-age facility, they have been carrying out time travel experiments for more than 40 years. A useful time travel particle is the muon. Muons are high-energy particles produced by cosmic rays, which constantly bombard the Earth's atmosphere. Muons live for only about 1/1,000,000th of a second. Here in CERN, scientists use speed to make these subatomic particles live longer, thereby turning them into time travelers. Giant accelerators like this one at CERN push the muons to velocities approaching the speed of light.
If we have a muon traveling in a ring at close to the speed of light, its lifetime is prolonged. That means that the clock, which the muon is ticking slowly, slowly, slowly. So when the muon comes back, it has only gone through tick-tack, 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 while we have gone tick-tack, 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 tick-tack. So in a sense, the muon is coming to our future, because only 1 second has elapsed for the muon, 20 seconds have elapsed for us.
Scientists enable muons to time travel into the future by slowing down the rate of time for muon. There is, however, a catch, which is the major roadblock to using speed to build a time machine. Any mass has an associated energy. As an object gains energy by moving at speed, its mass actually increases. The metal balls on this office toy weigh more when they are moving than when they are at rest. But because they are moving slowly, the increase in mass is very small. If they were moving at close to the speed of light, the increase in mass would be immense. In fact, a subatomic particle whizzing around the CERN accelerator close to the speed of light can weigh more than 7,000 times its weight at rest. As the particles get heavier, scientists at CERN must provide more and more energy to keep them moving.
As you increase the energy of the particle, you get closer to the speed of light. And then you double the energy and you get a little closer. And then you double the energy and you get a little closer. But you never go beyond. In order to reach the speed of light, you would need an infinite energy, which we happen not to have available.
If energy is the stumbling block of subatomic time travel, then imagine the scale of the problem for a human-sized time machine.
The main problem with using speed to time travel is that we can't move an object anywhere near to the speed of light. It would take all the Earth's energy resources just to push our rocket to a tiny fraction of the speed of light. But you wouldn't notice any difference unless you got very close to the speed of light itself. We simply don't have enough energy.
And there's another problem. Using speed to build a time machine is a one-way journey into the future. Traveling close to the speed of light will enable time travel to the future, but the time traveler has not mastered time. He has merely slowed down his own rate of time and fast-forwarded himself through time. He wouldn't be able to come back to tell his tale. There is, however, another way to build a time machine. Gravity. Many of us think of gravity as simply a force that keeps us on Earth. But scientists here at Manchester University in England view it in a totally different way. For the time traveller, gravity is evidence of how mass bends or distorts the space-time fabric. Professor Brian Cox is an expert on gravity and on how it interacts with space-time.
Space-time's not just, up there, it's here, it's in front of me and it's inside me. And I bend and curve it a little bit. I produce a little bit of gravitational force. But of course I'm very light, so when I move I don't curve it very much. But something the size of a star or a galaxy or a black hole warps and curves the space-time a huge amount.
The greater the mass of the object, the greater the impact or dent on the space-time fabric. This isn't just in theory, here's the evidence. These Hubble telescope images show what is happening to light as it travels through space. As light passes a galaxy, its path bends. By examining how light bends as it travels, we can prove that mass is bending space-time. This experiment replicates this phenomenon in a lab. It's a mini-universe, and it shows how light travels across space-time. In flat space-time, a light beam follows a straight line. But there is evidence that light is bending as it travels through the universe. The path it follows must also be bending, and that path is space-time itself.
Billions of stars are bending the space-time, acting like a lens. So a lens curves light, and if you bend the space-time, the light will curve. So you get the image of the galaxy in the middle, but then you get these really distinctive rings around. And that's strong evidence, overwhelming evidence, that mass bends space-time.
This warping of space-time will help us to build our time machine. When gravity bends space-time, it has a very real effect on how time passes. Here on Earth, we might not feel it, but time runs slower on the ground floor compared to at the top of a skyscraper.
The closer I am to the Earth, the more curved the space-time, the stronger the gravity, and the slower time ticks. Whereas here, space-time's a little bit less curved, gravity's weaker, and so time ticks faster. Now, it's a really tiny effect. If I was to stand at the top of this building for 100 years, then my watch would be 50 millionths of a second faster than somebody's watch down on the ground. So in a sense, the Earth is a time machine.
Take this into space, and the effect is even greater.
Yeah, I'd like to go to the university. It's M199QL. The fact that time passes at a different rate in orbit a long way from the Earth than it does at the surface of the Earth is really important for GPS or sat-nav, because that works by having synchronized clocks on the ground and in the satellites. And because the satellites are in a weaker gravitational field, time is passing more quickly. And actually, there's a time difference of 50 microseconds a day, which is 50,000 feet a day. So if you didn't correct for that and didn't take account of the fact that time passes at different rates, satellite navigation wouldn't work.
Earth's gravity and consequent warping of space-time isn't extreme enough to help a time traveller journey into the past. But there are places in the universe where gravity dramatically distorts space-time.
Most of space-time is nearly flat. It is only in black holes that it is strongly warped.
Professor Stephen Hawking is renowned as a world expert on black holes. Back in the 1970s, his groundbreaking research illuminated the then theoretical black hole. The gravitational pull of a black hole stretches and warps space-time around it to an incredibly deep cone-shaped hole. Because the gravity of the black hole is so intense, it drastically slows down time. Physicists like Hawking are fascinated by what a black hole does to time. But there is a catch. The black hole has a boundary called the event horizon, which leads down to the densest point, the singularity. Not good news for the time traveller.
In a black hole, you would be bound to hit the singularity and be crushed out of existence.
This is the Chandra X-ray Observatory. It's located 200 times higher than the Hubble telescope, and it provides scientists with new data on black holes.
Thank you, sir.
The mirrors on board this satellite are the smoothest mirrors ever constructed. Chandra sends back X-ray images 10 times sharper than the best previous X-ray telescope.
82 EPS.
That's the equivalent of reading a stop sign from 19 kilometers away. When scientists analyzed X-ray images of supermassive black holes, they discovered that they were spinning at close to the speed of light. This causes the space-time fabric to be dragged around. Scientists call this frame dragging. Space-time becomes so distorted that it forms an almost complete circle. Confirmation that black holes rotate was music to the ears of anyone interested in time travel. The time traveller was just about to strike gold.